So now let's go to the proof. So we want to use induction to show that triangulation is always possible. Our idea was that find a vertex that the angle is less than 180 and connect its neighbors. The first thing we want to see is that whether there is always a vertex like this. Why is there a vertex in the polygon whose angle is less than 180? There are many ways to prove this, but probably the easiest way is the following. Look at all the vertices of a polygon. One of them will have the smallest x coordinates, such as this one, right? So this means that there is no point of there is no vertex of the polygon on this side. So all of these vertices are over here. Okay. And in particular, it means that the neighbors of this vertex are also to the right. Since the neighbors are all both to the right, this angle cannot be bigger than 180. So it's at most 180. Okay. If it's exactly equivalent to 180, this is only possible if, like, say, the picture is like this, right? So the neighbors are on the line, vertical line, and then I could look at on all the vertices that are on the vertical line, look at the topmost, so let's say this one. Then only one of its neighbors can be on the vertical line, and the other one cannot be on this vertical line. So therefore, I will find an angle that is strictly smaller than 180. Okay. So in other words, this is always possible. So that's a good start. Okay, so we start with the leftmost point P and look at its neighbor Q1, Q2. We make the connection. If this connection is valid, then by induction we're done. We cut off this piece, and it's called an ear. We cut this ear, and then we are left with a polygon that has one fewer vertex. So then we can use induction. But it could go wrong, right? Like example, the picture could look like this, that when you connect the neighbors of this leftmost point, it actually cuts through the polygon. And in other words, there are some stuff that is in the way, and that's not a valid connection. So now we're kind of stuck. What can we do? The idea here is that we want to fix something. We want to use some of the geometric properties of what's happening here to show that we can make some other connection. So this connection doesn't work out, so maybe some other connection will work out. And the idea is the following. So look at this line segment. Okay, so the general idea here is that I want to find something that I can make a connection to. The idea is that sometimes it helps to look at extreme things with some measure, and sometimes they will have the property that I'm looking for. In this particular example, the extreme thing that I'm trying to find is the farthest distance away. So I look at this line segment and I look at the farthest vertex that exists inside this triangle that lies in this direction. First thing, why is there a vertex here? The claim is that there must be a vertex inside this triangle, because assume that there is no vertex inside this triangle. So if there is no vertex in this triangle, then we'll have a contradiction. And the reason is the following. So I have this triangle P, Q1, and Q2. And I know that this line segment intersects the boundary of the triangle. If it does not intersect the boundary of the triangle, then I'm good. So there is at least one vertex of the triangle that is intersected. Sorry, one segment of the triangle that is intersected, of the polygon that is intersected by this line segment. Based on the property of the polygon, I know that the polygon is simple. So this segment S that intersects the line segment Q1, Q2 cannot intersect the line segment PQ1 or PQ2, because these two are part of the boundary of the polygon, and S is also part of the boundary. Since the polygon is not self-intersecting, this line segment cannot intersect the boundary. So I have a line segment that intersects only one edge of a triangle. So therefore it must have a vertex inside the triangle. So what we have proved so far is that the triangle Q1, P, and Q2 contains a number of vertices. Since it contains a number of vertices, there is one that is farthest away from it. So let's look at that vertex, say this one. Okay. Now the claim is that if I connect P to Q3, then it cannot contain any vertex of the polygon. And again, the proof is very similar. Imagine, so now let's give this a label. So let's call this Q1 prime, and let's call this Q2 prime. If this triangle contains a vertex of a polygon, let's say a vertex of a segment S, then I have two cases. I want to claim that this line segment Q prime 1, Q prime 2 cannot intersect the boundary of the polygon. If it intersects the boundary of the polygon, let's say the boundary on the line segment S, then with a similar proof, I could show that there exists a line vertex of the polygon that is inside the triangle P, Q1 prime, Q2 prime. Therefore, I could find another endpoint of this line segment inside, and therefore I could find another line segment that is furthest away than Q2 from the line segment Q1, Q2. In other words, I could slide this line segment further away from this line segment and find the one that is more extreme. So therefore, if Q3 is the farthest vertex of the polygon that is inside this triangle, farthest away from this line segment Q1, Q2, then when I look at this smaller gray triangle, it has to be empty. It cannot contain any vertex of the polygon, so therefore this line segment cannot intersect the boundary of the polygon. And since it cannot intersect the boundary, therefore I can easily connect P to Q3. And once you make the connection from P to Q3, then the polygon is decomposed into two smaller triangles, so therefore by induction I could triangulate each one. And then we're done with claim 1.